So now we're going to run through a suite of, I'll pick a few of these in 3D examples, 3D Hex 8. We'll start out with the static simulation that has zero slip. So this is somewhat similar to what we ran in the debugging session where we ended up with zero slip. Then we'll run, let's see, we'll run the static simulation where we have slip, and then we'll do probably the step 13 and 14 where we have stick slip behavior. So here this is step 11. That's very similar to the step 03 when it ran properly in our debugging session. Here we put compression, 1 meter of compression on using a Dirichlet boundary conditions, 3 meters of lateral displacement, and then we're going to have the fault slip. So I think let's go and run this. That's not. Okay, so here let's go to 3D Hex 8. We'll look at the, I'll show you the parameters first. So we'll start with step 11. So we'll skip over the one where there's no slip. So static simulation. So total time of 0. Got a typo there. And it's very important now, in order, also detecting locked, is we use the slip rate. So we have to compute a slip and a slip rate because many fault constituent models depend on slip rate. So even though we're doing a static simulation, in order to get a reasonable slip rate that makes physical sense, we need to give it a time step that's comparable to the type of static simulation we're doing. So in this case, I put in 5 years. We're going to put in Dirichlet boundary conditions, X positive, X negative, and Z negative, fault interface, output to the domain, subdomain, output solution subset for the subdomain. Here's where we've changed our solver to the nonlinear solver. And here's our Dirichlet boundary conditions. So on the X and Y, X faces will constrain X and Y degrees of freedom. Here's our shear displacement. Sorry, that's the normal displacement. Here's our shear displacement of 3 meters. We'll fix the bottom boundary. Here's the faults, label the faults. Through-going faults, so we don't need to mark the buried edges. Static coefficient of friction, quadrature scheme. That was an error I forgot to put in. So I was going to show you what happens when you add the wrong quadrature scheme. Here's our uniform coefficient of friction of 0.6. Here's our sensitivity solve parameters. I've chosen to also display that converges, just in case it were not to converge. And then the output, we're writing to VTK output. Any questions on our inputs? Yes. Yeah. So in this case, I used a uniform database to specify the parameters for the friction model. So, step 11, I'm going to capture it to a log. And then we'll look at the output. Again, another case of a through-going fault, so it has, there's all the log summary. Look, yes, we converge absolute. Notice our nonlinear, our residual was going back. It was converging to our relative tolerance of 10 to the minus 19. So that's going a little farther than what we needed. What's our absolute tolerance here. Absolute tolerance 10 to the minus 20. We don't need that. So put that at 10 to the minus 13. I'm not sure why that is there. So I'm just going to run it again, make sure it still works. Should run a little faster this time. So in that case, I have my absolute tolerance much tighter than what it needed to be. There, you can see how it ran a little bit faster. Scroll up and we can look at where it ended up. Converged absolute tolerance. Nest tolerance is down to 10 to the minus, essentially 10 to the minus 9. Here's my friction solve interior. Internally, it was using 5 iterations. It converged. Here's the line search information that Matt was talking about before. So it looks like everything ran. We didn't get any errors. Let's see, where was that? So yeah, so what I want to do, what I actually want to do is I'm not going to change those, but let's get these. Let's use values consistent with what I was claiming we should use, advocating we should use. So let's do 10 to the minus 20, 10 to the minus, what did I say, 13. Well, we don't need to overwrite those. So we can do something like that. We can easily run it again. So Charles likes using T, and I just dump it all to step, and then I use tail to get the updates. Sorry. Yep. So nonlinear solve this time, S norm relative. So it basically we're down now to sort of the same order of magnitude, but it decided that the residual wasn't moving enough. So it stops. You'll notice that the linear residual is starting out at 10 to the minus 10, goes down to 10 to the minus 14. So it's essentially, there's not much going on because the linear solve is already down at essentially 0. So now we can look at what this looks like. So the defaults, so I can go in here and I can say PyLith problem interfaces faults. I think I have this. What did I forget? Oh, I forgot the step 11. So my zero tolerance, the default value is 10 to the minus 10. I thought one time we had 10 to the minus 12. I think I said, well, that's really it's a little too tight. No one really would use that in practice. So it's 10 to the minus 10, and so let's see here. So if I use 10 to the minus 10, then let's back this off to 10 to the minus 9, and let's do 10 to the minus 11. So up here I can sort of, I could do something like, this is within my fault, so I would put, say, something up here like zero tolerance equals 10 to the minus 10. So there, I use the same as the default value. We can run it again. No reason not to. Whoops. So now with those tolerances, now I've gotten down to, it's back to an absolute convergence with essentially the nearly the same order of magnitude in the SNES residual. So these tolerances can change things a little bit. Sometimes you'll get a slightly different convergence criteria depending on exactly what is used. But in general, the main thing I'm looking at is that my SNES tolerance is down to a small value. It's not 10 to the minus 4, it's 10 to the minus 10. It converged to absolute tolerance. My linear solve is the residuals are smaller than my nonlinear solve residuals. That's good. This is the type of behavior I expect to see when things are converging properly. So let's see. 30 hex 8 outputs. Well, my step 11. Warp it by a factor of 2,000. Whoa, maybe not 2,000. There we are. So this domain is much smaller than my debugging version. That's in the debugging session domain. So that's why I need to use a smaller exaggeration. So there you see we deformed. If I do the outline of our original, so there was our original, let's color this by displacement in the y direction. So here you can see what I did. I squished it in to get a normal traction on the fault, and then I also had lateral displacements on the sides to give it a shear, and then I had a little bit of slip corresponding to reducing the tractions down to a coefficient of friction of 0.6. I can check that by bringing up the faults. So step 11, let's bring up the fault solution. Turn off. So here's my fault, and I can use the calculator and say, give me the, and here, so pair view, if it sees 3 components, it says X, Y, Z. Normally that's right, but for the faults, we give information in terms of lateral slip, the horizontal, the reverse direction, and then the opening. So even though it says X, Y, Z, these are not X, Y, Z components of slip. They are the first, second, and third components of the slip vector, which are done in terms of the fault coordinate system of left lateral, reverse, and opening. So I'm going to use the shear, first component is the shear component, and I'm going to divide that, take minus that divided by the normal component, which is the Z component. Show what that looks like. You'll see that at the corners, or for almost all the domain, it's 0.6. That's what we want. That's consistent with our coefficient of friction of 0.6. You notice the corners are slightly different, and that's because if I look at what my tractions are, there's my shear, there's my up dip, down dip traction vector. So at the corners, because I have the free surface, things get a little, they're not purely horizontal, and then on the normal direction, I have some variation. So if I go back and show what my calculated result of looking to see if things are consistent with my coefficient of friction of 0.6, they are. So my tractions are consistent. I can also show the slip. There's the slip magnitude. So I had, near the middle, I have 1.82 meters of slip. Out the outside, it's down to about 0.9. That's the slip magnitude. There's the x direction, so it's dominated by lateral slip. There's a little bit of, symmetric in the y component. Remember, I'm pinning the bottom of the fault, or the bottom of the domain, except for the fault opening, 0 fault opening, just what we would expect. Any questions on this example? In terms of the, we can check, we can look at that. So let's come down here and let's do 10 to the minus 6. So that's a pretty big difference. Oops. One thing I'll converge faster. So let's see. So here we are. Let's delete the calculator, delete the, so we can, here's our warp domain. So let's put it in terms of wireframe view. Then let's bring in our new one. So step 11, let's exaggerate it by, so warp it, I think I did 500. You can see there's a very, very little difference in this case. So here, you can sort of say, well, what are the magnitude of my observations? How close are they together? What sort of spatial scales am I resolving? What's the uncertainty in my observations if I have GPS displacements for a really large event that have uncertainties of, maybe a couple centimeters? There's no reason to drive my solution to have an uncertainty or errors on the order of a millimeter. So, you saw how it ran a little faster, fewer iterations. So that's something to sort of keep in mind. You don't need to drive everything down to 10 to the minus 10. You can drive it down sort of on the order of 10 to the minus 6.
Notice that the nonlinear tolerances have physical units. They're about how accurate the quantities are, but the linear tolerances are not. The linear tolerances are only to accelerate the
Okay, so that's, any other questions on this?